Hi everyone, and welcome to week 5 of Introduction to Logic. This week we are going to be continuing our foray into the natural deduction proof method for propositional logic, and we're going to be covering the second batch of implication rules from the Fruhling logic textbook. Now, the first thing I want to say is that these new rules that you're going to learn today are in addition to the previous rules. And in general, this is going to be true. Week after week, you're going to learn a new batch of deduction rules, and those rules are cumulative. They're in addition to the rules that you've learned previously. So our system of natural deduction rules is going to grow and grow and grow. So without further ado, let's dive in to talk about the first rule of implication, first new rule of implication called simplification, abbreviated SIMP. And the rule basically works like this. If you have a conjunction on its own line, something like P dot Q with a dot as the main operator, you can take the term on the left-hand conjunct, and write that on its own line. And if you take the time to think about what a conjunction means, I think you'll see why this rule works. P dot Q means P is true and Q is true. And if both P and Q are true, then obviously P has to be true. So you can take the left-hand conjunct and write P on its own line. Just as a reminder, P and Q here in these argument forms could stand for something simple or it could stand for something compound. So for example, if you have a statement like P dot Q and R or S, any compound statement with a dot as the main operator, on the next proof line, you can take the left-hand conjunct, which in this case would be this entire expression in parentheses on the left, and you can bring the left-hand conjunct down and write it on its own line, so P dot Q on its own line. And in general, these argument forms are given in terms of P and Q, but P and Q are statement variables that stand for any statement, whether simple or compound. The next rule is conjunction. This is also a fairly straightforward rule. If you have two statements on their own lines, P and Q, then you can conjoin them together with a dot to get a statement like P dot Q. In other words, you can take any two statements on any previous lines and conjoin them together with a dot, whether simple or compound. So for example, if you had A and B on one line, and you had C implies D on another line, you could conjoin those two statements together on the next line of the proof using a dot. So you would get something like A dot, you would get something like A dot B in parentheses and C implies D in parentheses, using a dot to conjoin the two together. So conjunction is pretty straightforward. You can take any two lines of a proof, conjoin them together with a dot on a new proof line. The next rule is called addition, abbreviated ADD. This rule is a little counterintuitive because you can see that the conclusion contains a letter that the premises don't contain. So you can take any statement on its own line, here P, and you can add a new statement onto that line using a wedge to get something like P or Q. And if you take the time to think about what this argument form means, I think you'll see why this works pretty easily. If P is true, no matter what Q is, whether it's simple or compound, whether it's true or false, P or Q is always going to be true because at least one of the two conjuncts, P, is already true. So it doesn't matter what Q is. The thing that's counterintuitive about this rule is it lets you add in a new element, a new letter, or a new compound statement into a proof that didn't necessarily come from anything above. But no matter what P is, if P is true, that's what a given premise tells us, that a letter on its own line is true. You can take any letter or any compound statement, disjoin it onto that previous statement using a wedge, and the end result will always be true. So let's do a simple example and a complex example. So for example, if I had A on its own line, I could conclude several things from that. I can conclude A or B, A or C. I could even disjoin something compound like A or B and C. Because if A is already true, it doesn't matter what you're disjoining on using the wedge. A or anything else will be true. And then this also works if P is complex. So for example, if you have a statement like A and B on its own line, you could use a wedge to get A and B or C. You could use a wedge to get A and B or anything you want, anything you can put in parentheses or brackets here. C implies D, anything you like. All of those are going to be instances of addition. And we'll see how this works in the context of proofs momentarily. It's a little confusing because you have to be strategic about what exactly you're adding into the proof, something that's going to be productive towards reaching the overall conclusion of the proof. And we'll look at some examples of this momentarily. The last rule that we're going to look at today is called Constructive Dilemma, abbreviated CD. This is a fairly scary looking rule because there are a lot of components to it. And oftentimes to use this rule in the context of a proof, you need to be a little strategic to set up the statements so they have this form so you can apply this rule. And again, we'll look at examples of that when we dive in to do some examples momentarily. But the rule basically works like this. If you have the conjunction of two conditionals, like you see here in the first line, P implies Q and R implies S, that says the two terms P and R each imply something. P implies Q, and it's the case that R implies S. And on the second line tells us that one of those two antecedents is true. Either P is true or R is true. And again, I want you to take the time to think about why this rule works. If one of two things is true, either P or R, and each of those implies something, the first premise tells us that P implies Q, and the second premise tells us that R implies S, and one of those two antecedents is true, then obviously one of the two consequents, Q or S, would have to be true. And that's what the conclusion tells us. What's tricky about using this rule is setting up the statements within your proof to match this form so you can apply this rule. And again, we'll look at some examples of that momentarily. So I want to make this video as brief as possible so you can get as much time on the homework as possible. So I'm going to dive in and start doing some sample proofs for you so you can see these rules in action. So this proof here, we're given three premises. Not M implies Q on line 1. Line 2 tells us that R implies not T. Line 3 tells us that either not M or R. And the conclusion that we're trying to show is Q or not T. And just to reiterate the whole concept of doing a proof, this should be obvious after having done the homework for last week, but the idea is that you deduce, given these premises, you deduce further statements that have to be true using these deduction rules, both these and the ones from last week. And when you're able to obtain the conclusion on its own line, we're done and we'll have shown that that conclusion necessarily follows from those premises. So let's dive in. We're going to add a new line, line 4. And what I see right off the bat is that on line 3, one of two things is true. Either not M is true or R is true. Either not M is the case or R is the case. That's what the disjunction tells us on line 3. But lines 1 and 2 tell us that each of those two terms, each of those two disjuncts implies something. Not M implies Q and R implies not T. And this is starting to look an awful lot like a constructive dilemma. We have a disjunction. Each of the two disjuncts implies something else, but we need to set it up so it looks like the form of a constructive dilemma. And I'm going to write constructive dilemma over here on the side just so you can remember what it looks like. In order to do constructive dilemma, we have to have something that looks like this. P implies Q and R implies S, two conditionals that are conjoined together. And we need to know that one of those two antecedents, P or R, is actually true. And if we have that, we can get something like Q or S. So we have our two conditionals. We know that not M implies Q. We know that R implies not T. But we need to make it look like this form for constructive dilemma, which I'm going to write here, constructive dilemma. So we need to take those two conditionals and conjoin them together using the dot. And we have a rule for that. We have the conjunction rule that lets us take any two lines and conjoin them together on a new line. So the first term here in the disjunction on line 3 is not M, so that's the conditional that's going to come first. So in line 4, we're going to have not M implies Q. Here's our dot, and we're going to add line 2 now. R implies not T. And that is going to follow now from lines 1 and 2 by conjunction. And remember, conjunction lets you take any two previous lines and connect them together with a dot. And I want to reiterate why this makes sense, right? If line 1 is true and line 2 is true, then obviously both of the statements on those two lines, the conditional on line 1 and the conditional on line 2, are going to be true. And that's what the dot means. Both of those two expressions are true. And now we're getting something that looks an awful lot like the form of constructive dilemma. We have a disjunction on line 3, either not M or R. On line 4, each of those two terms implies something. Not M implies Q, and R implies not T. So according to constructive dilemma, one of the two consequence, Q or not T, would have to be the case. Q or not T. And that now is going to follow from lines 3 and line 4 by constructive dilemma, C, D. If it's not clear why this is working, have your textbook open or reverse the video and go back and look at the form for constructive dilemma. Compare statements 3, 4, and 5 here with the form for constructive dilemma, and you should be able to pretty easily see why this rule works in this context. Okay, so this is a pretty typical example of the kind of mechanics you have to do within a proof to be able to set up a constructive dilemma. In order to be able to use a rule like constructive dilemma, it has to match the form exactly. You have to have a disjunction, and each of those two terms has to imply something else by a conditional, but those two conditionals have to be conjoined together with a dot. And from those, you can conclude that one of the two consequence, in this case, Q or not T, would have to be the case. Okay, let's move on and do some more proofs using the new rules. In this proof, we're given 3 premises. N implies both D and W on line 1. Line 2 tells us that D implies K. Line 3 says N is true, and we're trying to show that N and K are both true on its own line. So let's dive in. We're going to add a new line, line 4. And this proof makes the point pretty clearly that the system of rules is cumulative. Right off the bat, from the homework from last week, you should see that line 1 and 3 will give you a modus ponens step, right? Line 1 says if N is true, then that expression in parentheses, D and W, would have to be true. But line 3 says N is actually true. So from that, we know that D and W has to be true. That's going to follow now from line 1 and line 3 by modus ponens. That's one of the rules that we covered last week. Okay. Well, line 2 tells us that D implies K. And in order to basically use that statement, we need to know that D is true. And we know that D is true from line 4. Line 4 tells us that D and W are both true, but we need D on its own line. So this is going to be an instance of the simplification rule. If D and W are both true, then obviously D is going to be true. Structurally, we have a conjunction, D and W, connected by the dot. And whenever you have that, you can simplify this term to bring D onto it, bring the left-hand conjunct, in this case D, down on its own line. And that's going to follow from line 4 by simplification. Notice that we're only citing one premise, and some of these rules cite one premise, some cite 2 premises. This is an example of a rule where you only need to cite one premise. Line 5 follows directly from line 4. It's not a combination of multiple premises. Okay, once we know D is true, line 2 tells us that D implies K. And this is going to be another fairly simple modus ponens step. So we're going to get K on its own line, and that's going to follow now from line 2 and line 5, again by modus ponens, one of the rules from last week. Whenever you're doing a proof, you constantly want to be looking at the conclusion, because the conclusion is going to guide you towards reaching your goal, which is to get the conclusion on its own line. So in order to get the conclusion, we need to know that N is true and K is true. That's what the conclusion says, N and K. Well, we have those on their own line. We have N on line 3 now, and we have K on line 6. All we need to do is conjoin them together. And according to the conjunction rule, you can take any 2 previous lines and connect them together with a dot to form a conjunction. So on line 7, we're going to get N dot K, and that's going to follow from line 3 and line 6 by conjunction, C-O-N-J. And we're done. Once we've got the conclusion on its own line, we're done. And we've shown that that conclusion necessarily follows from those premises, because each of these steps is a valid argument form yielding something that has to be true given the truth of the premises you're given. Okay, next example. Okay, so we're given 3 premises. The first is a conditional. Notice that the main operator is that horseshoe. The antecedent is H or not B. So if H or not B, then R is the case. Line 2 says, it's another conditional. If H or not M, then P. We know H is true, and we're trying to get the conclusion now, R and P on their own line. Let's dive in. The thing that I notice right off the bat is I know H is true, and using the addition rule, I can add anything I want onto H using a wedge, and I'm going to end up with a line that follows. And again, just to reiterate the addition rule, if you have a statement P, you can add anything you want, P or Q, where Q stands for anything at all that you want. It doesn't have to come from anything above using a wedge. Now you want to do this strategically, and I'm going to do an example of this and talk about why I did that. So from line 3, I'm first of all going to get H or not B. So I'm choosing here to add on this junk, not B, onto H using a wedge. And that's going to follow from line 3, just line 3, by addition. And the reason I chose to add not B onto H using the wedge is that gives me the antecedent of this conditional in line 1. From there, I can do a modus ponens step and eventually get R on its own line, which is half of what we need for the conclusion. Notice now that I could do the same thing for premise 2. I could add not M onto H using a wedge, and that will give me the antecedent for this conditional in line 2. After that, I'll be able to do a modus ponens step, and that will give me P, which I also need for the conclusion. Once we get R and P on their own lines, we can conjoin them together and get this conclusion, R and P. So it's just a matter of cranking out what I just described. But here, the thing I really want to draw explicit attention to is that you can disjoin anything you want onto a previous statement using a wedge, but you have to do it strategically. You have to do it in a way that's going to be productive for letting you do a subsequent step of the proof. In this case, we're adding on not B onto H so we can get the antecedent of this conditional in line 1 so we can do a modus ponens step. Okay. Let's do that modus ponens step since we just talked about it. Once we have H or not B, from line 1 and line 4, we can get R on its own line according to modus ponens. So R is going to follow from line 1 and line 4 by modus ponens MP, one of the rules from last week. And as we just described, we're going to do the same thing so we can end up using premise 2, but in this case, we need to add not M onto H. So we take H, which is on line 3, we're going to add a wedge, and we're going to add whatever we want, but in this case, we're going to add not M, so we can get the antecedent of that conditional in line 2. And that is going to follow from line 3 by addition. In other words, if H is true up here on line 3, then H or anything else would follow from that according to the addition rule right here. So we added not M onto H. That came directly from line 3 by addition. I'm going to do just a little bit of cleanup here. There we go. Okay, once we have H or not M, we have the antecedent of that conditional on line 2. So from modus ponens, we can get P on its own line, and that's going to follow now from line 2 and line 6 by modus ponens. And we're very nearly done. In order to get the conclusion, R and P, we needed R on its own line and P on its own line. Once we have each of those two conjuncts, we know each of them is true, we can connect them together with a dot according to the conjunction rule. And that's the last step we're going to do in this proof. R and P. And that's going to follow now from line 5, which tells us R is true, line 7, which tells us P is true, by conjunction, C-O-N-J. And we're done. Once we've got the conclusion on its own line, we are done with that proof. Okay, fairly straightforward, but this proof is important to look at because it demonstrates the need to use addition strategically to add on something to a previous statement using the wedge in a way that's going to be productive towards completing a subsequent proof step. In this case, we did it so we could set up subsequent modus ponens steps. Okay, let's do another example. It's the theme of the day, lots and lots of proofs. And in general, I just want to take a moment to reiterate that you really need to be getting lots and lots of practice with these proofs. Proofs are cumulative. They're pretty elegant. I think you can see it doesn't take much mental effort to power through one of these proofs. But our system of rules is going to continue to grow, and the complexity of the proofs is going to continue to grow. So you need to get lots and lots of practice. Do as many proofs as you can. Do the ones I'm doing in this video. Do the ones I assigned for homework. Do examples you can find. Do all the examples from the textbook chapter. And if you do that, you should be well prepared to move on next week when we add even more rules to our system of proofs, system of deduction rules. Okay, so we're given two premises. The first premise is a conditional. The main operator is that horseshoe. The antecedent is L or T, and the consequent is B and G. So reading line 1 in natural language, it would be something like, if L or T, then B and G. Line 2 tells us two things are true, L and K is equivalent to R. And the conclusion we're trying to show is L and B, or L dot B. It's always good to look at the conclusion and think about how you might go about getting that conclusion. Whenever you have a conjunction like this in the conclusion, the thing that should obviously come to mind is that, well, in order to show that L and B are both true, you're going to show that L is true and show that B is true. And if you can show both of those two terms independently, you can conjoin them together with a dot and show that L dot B is true. Well, happily, in line 2 tells us that L is true and K is equivalent to R. But in line 2, we have a conjunction. Two things are true. L is true, and that expression in parentheses, K is equivalent to R, is true. And whenever you have a conjunction, you can take the left-hand conjunct and write it on its own line. So line 3, we're just going to write L, and that's going to follow from line 2 by simplification, S-I-M-P. Right? Obviously, if L is true and K is equivalent to R, then L is true, and we get that on line 3. Okay, new line, line 4. The next thing I notice is that once we know L is true, we could use addition to get L or T, basically adding on that expression T right onto L using that wedge, because if L is true, then either L or T is going to be true, because one of the two conjuncts, or excuse me, one of the two disjuncts, in this case, L will be true, right? If L is true, then obviously either L or T is going to be true. So in this case, L or T is going to follow from line, you have to be really careful here. It does not follow from line 1. It follows directly from line 3. If L is true, then either L or T is true. So it follows from line 3 by addition. And again, just to really drive this point home, the reason that we chose to add T onto L using that wedge is so we can get the antecedent of this conditional way up here in line 1. It doesn't follow from line 1, but it follows from line 3, like I just mentioned, but we're doing it so we can get the antecedent of that conditional in line 1. Once we have L or T, pretty clear, this should be obvious now at this point, given your homework from last week, but once you have the antecedent L or T, then we can do modus ponens to get B and G on its own line. And that's going to follow from line 1 and line 4 by modus ponens. Again, just to really drive this point home, and make even these obvious steps a little more intuitive, right? Line 1 said that if L or T is true, then we know that B and G have to be true. In order to do modus ponens on that and get B and G on its own line, we had to have that antecedent, L or T. We knew that L was true. We got that on line 3. And according to the addition rule, we can use a wedge to add anything we want onto a previous statement using a wedge. And so we chose to add T onto L and get the statement on line 4, L or T, so we can get that antecedent of the conditional in line 1. And that will allow us to plow forward through this proof. The rest of this proof should be pretty straightforward. Okay, line 6. So we're trying to get L and B. That's the goal. That's the conclusion of the argument. Well, we have L on its own line. Now we need B on its own line. But line 5, the line we just added, says that B is true and G is true. It's a conjunction. And whenever you have a conjunction, you can take the left-hand conjunct and write it on its own line, in this case, B. And that's going to follow from line 5 by simplification. Now we're almost done. We said that in order to show that the conclusion is true, we're going to get L on its own line, B on its own line, and then connect them together with a dot using the conjunction rule. Well, we have that. On line 3, we have L. On line 6, we have B. So we're going to conjoin those together with a dot, L and B. And that's going to follow from line 3 and line 6 by conjunction. and we're done. Once we get the conclusion on its own line, we will have shown that the argument is valid. Fairly straightforward, but you can see, most importantly here, you need to think strategically. Some of these rules, like addition and constructive dilemma that we looked at in a previous example, you have to be really strategic. You have to think ahead about why you're using that rule and what you want to add in using the addition rule to set up a subsequent step. In this case, we were doing it to set up this modus ponens step here on line 5. Okay, next example. In this example, we're given 3 premises. The first is a conjunction. It says N implies B and O implies C. Line 2 tells us that Q implies something. Q implies N or O, that expression in parentheses, which we don't have to worry about very much just yet. And line 3 tells us that Q is true, and we're trying to get the conclusion B or C. What I notice here is that the conclusion is a disjunction, B or C. So that looks a lot like the conclusion of a constructive dilemma. So my guess here, not having done the proof yet, is that the conclusion is probably going to follow by a constructive dilemma, or we're going to use a constructive dilemma step somewhere inside this proof. But we'll see how it unfolds. I think that's the fundamental challenge about doing proofs. As proofs get more complex and as you get more rules added to our system of rules, moving forward through a proof is really going to be a matter of keeping in mind the conclusion, thinking strategically about what kind of steps are going to be necessary to get to that conclusion, and what you can do given the premises you have or the statements that are already in your proof and the system of rules you've got. And hopefully they come together in the middle somewhere, that when you start applying some rules that you see that are easy to apply, the path towards obtaining the conclusion will become sort of easier to see as you move forward through the proof. It's not always going to be the case that you're going to see immediately what's going to lead to that conclusion. Sometimes you just have to dive in, start applying rules that you see follow from the premises very naturally, and hopefully the path that you'll take to get to the conclusion will become clear just in the course of doing the proof. In this case, I see a pretty obvious starting point. Line 2 says if Q is the case, then we're going to get N or O. And line 3 says Q is true. So from lines 2 and 3 by modus ponens, which is probably the easiest, most friendly rule we've got. You know, every time you see modus ponens, you're going to rejoice a little bit because it's such an easy step. But yeah, from lines 2 and 3, we're going to get N or O by modus ponens. So from line 2, 3, MP, modus ponens. Our old friend, modus ponens. Okay. What I notice next is that line 4 is a disjunction. It says either N is true or O is true. But line 1 tells us that each of those 2 terms implies something. Line 1 says that if N is true, you get B, and if O is true, you get C. So if one of those 2 antecedents, N or O, is true, obviously B or C, the 2 consequents, one of the 2 consequents would have to be true, B or C. And this is merely a matter of pattern recognition. You have to be able to see that you've got a disjunction and each of those 2 terms implies something else up here on line 1. If you don't see that, pause this, take a look at this argument as it is right now, look at the form for constructive dilemma from your textbook or previously in the video, and you'll see that they match. So this is going to follow from line 1 and line 4. Actually, I'll do this in a different color for consistency's sake. It's going to follow from line 1 and line 4 by constructive dilemma, CD. And notice we're done. That is the conclusion, B or C, and we don't have to do anything else. A very, very short proof. Might have been a little hard to see how to get B or C from what was given, but hopefully you can see now, given that line 1 and line 4, either B or C would have to be true according to constructive dilemma. Hopefully that's easier to see. Okay. Next example, we've got 3 premises. First is a conditional. It says if either D or E, then G and H. Line 2 tells us that G implies not D. Line 3 tells us that D is true and F is true. And we're trying to get M on its own line. Okay, let's dive in. We're going to add a new line, line 4. One of the things you should almost always do whenever you see a conjunction on its own line you should almost always use simplification to simplify simplify it and get rid of that conjunction. The way you do that is to get the left-hand term on its own line, in this case, D. So D is going to follow from line 3 by simplification. Now, obviously, if D is true and F is true, F is going to be true as well. But the rule only lets you bring down the left-hand term. And there's a rule that's coming in a week or two that lets you switch around the order of a conjunction, because kind of obviously, if D and F is true, then F and D is true. But there's a separate rule that lets you switch around the order of a conjunction. You just don't have that rule yet. So for now, you can only bring down the left-hand term. Okay, line 5. Once we get D on its own line, the next thing I notice is that, well, if we knew that D or E were true, then we could do modus ponens and start to break apart line 1. Well, we know D is true, so according to the addition rule, you can add anything you want onto a previous statement using the wedge, and that statement will follow. So we know D is true, so D or E has to be true. And again, you have to be really careful here. This does not follow from line 1. This follows directly from line 4. If D is true, then D or E would have to be true. And that's going to follow now from line 4 by addition, ADD. Okay, once we have D or E, that's the antecedent of this conditional in line 1. That's why we added E onto D in the first place using addition. That's going to let us do modus ponens to get the consequent of that conditional, G and H, on its own line. And that will follow from line 1 and line 5 by modus ponens, MP. Well, now we have another conjunction on line 6, G and H. Well, if G and H is true, G has to be true. And that's going to follow from line 6 by simplification. And whenever you see a conjunction, you should almost always separate that out and bring the left-hand term down. Okay, well, line 2 tells us that if G is true, not D has to be the case. So we're going to get not D on its own line from line 2 and line 7 by modus ponens. So this is a really tricky proof from here. I want to pause here and draw some explicit attention to what's going on. What I notice here is that the conclusion M doesn't appear anywhere in the premises, if you notice. That letter M doesn't appear. So we're going to have to add in that letter M into the proof somehow in order to get that conclusion. What I notice next is that on line 4 we've got D, on line 8 we've got not D, which tells me that there's a contradiction somewhere in this proof. And an interesting quirk of logic is that anything follows from a contradiction. I think you'll see why, right? What it means for an argument to be valid is that it's impossible for the premises to be true and the conclusion to be false. So if you have a contradiction in the premises, obviously those premises will never be true together. If the premises contradict each other, they can't be true. So anything will follow from that. The way we're going to mechanically force our way through this in the proof is a little strategic. I want you to make sure you're paying attention to what I'm doing here. If you need to, watch this section of the video again. So we have D on line 4. We know we need M in the proof, and we know D is false on line 8. So we can use addition to add M onto D, D or M. And that's going to follow from line 4 by addition. The reason we did that is so we can set up a disjunctive syllogism. If we know D is false, we then know M has to be true. So on line 10, we know M has to be true on its own line. And that's going to follow from line 8 and line 9 by disjunctive syllogism. But our ability to do that depended on a couple of things. We needed to see that M was not in the proof. We needed to see that we could add M into the proof somewhere using addition. And we added it onto D here because we knew that D was false on line 8. So if we have D on its own line here in line 4, we added M onto that using addition. We know that D is false, so we know that M has to be the case. Of all the rules you're going to learn through the rest of the course, addition is probably the hardest rule to learn. And that's because you have to use it strategically. You can add anything onto any other statement using a wedge, but you have to see what's going to be productive towards reaching the conclusion. In this case, we needed to see that once we had D and we knew that D was false, we could add M onto D, and we know that we can do a disjunctive syllogism step. You have to be able to think 2 or 3 steps ahead like that to be able to do proofs, and that's just a matter of training yourself to recognize how to use these rules strategically. And I can't make you do that from watching a single example. You know, hopefully these examples we're doing in this video help, but you have to brute force your way through the homework exercises to get practice applying these rules strategically. If you don't get lots and lots of practice on that, the next few weeks are going to be very, very challenging for you. Make sure you get lots of practice using these rules strategically. And definitely let me know if you're having any trouble. If you're unable to complete some of the proofs in your homework exercises, make sure you let me know so we could jump in a Zoom meeting and look at them together so I can give you some guidance on how to use these rules. Okay, let's move on and do more proofs. Okay, in this example, we are given 3 premises. The first is a conditional. If P then R implies that if M then P. Line 2 tells us if P or M, then P implies R. Line 3 tells us that P or M is the case, either P or M, and the conclusion here is R or P. And I don't, off the top of my head, see exactly how we're going to get that conclusion. So we're going to start diving in, see what we can do, and then see if we can discern what's going to be productive towards reaching the conclusion. I see one thing right off the bat that may help. Line 2 says, if P or M, then that expression in parentheses, P implies R. But we do know that P or M is the case. That line 3 tells us that. So we can do a modus ponens step to get P implies R. And that's going to follow now from line 2 and line 3 by modus ponens. But P implies R also implies something. On line 1 tells us that if P implies R, then M implies P. So we're going to do the same thing with line 1 and 4. That's going to give us M implies P. And that's going to follow from line 1 and line 4 by modus ponens. And all of this should be reviewed. These, we covered modus ponens a week ago, and you should already have had lots of practice on modus ponens steps. So I'm not going to explain those too much at this point. Okay, the next thing I notice is that on line 3, we've got a disjunction, P or M. Lines 4 and 5 tell us that each of those 2 disjuncts, P and M, imply something. Line 4 says P implies R, and line 5 says M implies P. This is starting to look a lot like a constructive dilemma. But in order to use constructive dilemma, those 2 conditionals have to be conjoined together in order for it to match the form of the rule. So let's do that. And because P is the left-hand term, we're going to start with the conditional on line 4. So P implies R. I'm going to put some parentheses around that. And we're going to take line 5, M implies P. And that's going to follow from lines 4 and 5 by conjunction. Basically, we took lines 4 and 5, connected them together with a dot. But this is a perfect example of how you have to apply rules strategically. The whole reason we did that, you didn't have to do that. It's the only way we're going to get through this proof, but there's nothing from the premises above that tell us that we have to do that. The reason that we did that is so we can apply constructive dilemma. And what is constructive dilemma? You need a disjunction, which we have here on line 3, P or M, and we need the conjunction of 2 conditionals. Each of those 2 terms has to imply something. P implies R and M implies P. So from that, we can conclude that one of the 2 consequents, R or P, has to be the case. R or P. Happily, that is the conclusion, so we're done. We just need to cite where that came from. That would come from line 3 and line 6 by constructive dilemma, CD. So again, there's nothing particularly challenging about this proof, but it does hinge on your ability to see that in order to get that conclusion, you're going to have to set up this constructive dilemma. All the elements are there. You've got a disjunction. On line 4 and 5, you have these 2 conditionals. Those fell out of the proof pretty easily, according to these modus ponens steps. But you have to conjoin those 2 conditionals together in order to be able to use constructive dilemma. If you don't see that, you're not going to be able to use the rules correctly to reach the conclusion. So again, especially with addition and especially with constructive dilemma, those rules have to be used extremely strategically. And you might have to do a couple of previous preliminary steps in order to be able to set up the form of those rules to use those rules correctly. Make sure you get lots of practice on that in your homework. Okay, next example. We have three premises. F implies not T and A. Line 2 tells us that if not T or G, then H implies T. Line 3 says F and O are both true, and we're trying to show this conclusion, not H and not T. Let's dive in and see how we're going to do it. The thing I noticed right off the bat is that we have a very easy natural starting point. Line 3, we've got a conjunction, F and O. Well, if F and O is the case, then F has to be true. That's going to follow from line 3 by simplification. Whenever you see a conjunction, you should almost always use simplification. Not always. And if you end up with an extra line or two in your proof, that's okay. It just means your proof is a little longer. But as long as every step is validly applied, that's okay. You don't have to be a minimalist about this. Use the bare minimum amount of steps it takes to reach the conclusion. You know, in some logic classes with some logic professors, they might force you to be minimalist and have no extra steps in your proof. I'm not that strict about that, honestly. As long as every rule is applied validly and every step follows, then your proof is going to be a perfectly valid proof, even if you have extra steps in there that you didn't actually need to apply. So don't overthink that too much. Well, once we have F on line 4, line 1 tells us that if F is the case, then we get that expression in parentheses, not T and A. Well, F is the case on line 4, so on line 5, we're going to get not T and A. That's going to follow now from line 1 and line 4, excuse me, almost made a typo there. Line 1 and 4 by modus ponens, MP. Okay. Well, we have another conjunction, not T and A now. So let's simplify that and get not T on its own line. That's going to follow from line 5 by simplification. Here's where we have to start thinking strategically. Line 2 tells us that if we know not T or G, then we get that expression in parentheses, H implies T. Well, we have not T, and we know from the addition rule that we can take any statement on its own line, use a wedge, and connect anything at all to it, even something that didn't necessarily come from the proof above. So that's what we're going to do here. We have not T on line 6, so we're going to get not T or G. And we're doing that strategically so we can get the antecedent of that conditional in line 2. That's going to follow not from line 2, it's going to follow from line 6 by addition. Right? If not T is the case, then either not T or anything else would be true. Okay, the rest should be pretty straightforward, but let's crank through it. Line 2 tells us that if we have not T or G, we can get H implies T. So we're going to write H implies T on its own line. And that's going to follow from line 2 and line 7 by modus ponens. Well, again, this is a good place to pause and look at the conclusion. The conclusion that we're trying to reach is not H and not T. And if we can get each of those two conjuncts, not H and not T on their own lines, then we can connect them together using the dot and the conjunction rule. We already have not T, so now the goal is to get not H on its own line so we can connect not T and not H together with a dot. This is going to be pretty straightforward, but we're going to have to use the rules from last week. So for example, on line 8, we've got H implies T. On line 6, we know that T is false. The consequent of that conditional is false. From that, according to Modus tollens now, MT, we know that H has to be false. The antecedent has to be false. Again, this should be a review from last week, so I'm not going to dwell on that very much. If you need a refresher, go back and review Modus tollens from last week. Okay, and that's going to follow from line 6 and line 8 by modus tollens, MT. We've got our two conjuncts now. We've got not H on its own line. We have not T on its own line. All we need to do is connect those together with a dot and we're done. So not H and not T. And that's going to follow from line 6 and line 9 by conjunction, C-O-N-J. And we're done. We've got the conclusion on its own line. We've shown that that argument is valid. So the key move here that let us move forward is recognizing this addition step, recognizing that we needed to add something strategic onto a previous statement in order to do something else. In this case, we knew not T was the case. If we added G onto that using addition, that's what we did in line 7, that would give us the antecedent of this conditional in line 2, and that let us move forward and use modus ponens on line 2, and then the rest of the proof is pretty straightforward from there. But you have to use addition strategically. If you don't see that, you're going to get stuck and you won't be able to move forward and do subsequent steps that will be necessary to reach the conclusion. Okay, let's do a few more examples. Okay, in this argument on line 1 is a conditional. It says if C or not G, then not P and L. Line 2 says if not P and C, then C implies D. Line 3 says two things are true, C and not R. And the conclusion we're trying to show is D or R. So let's add a line 4. The very first thing I would do is simplify that expression in line 3, which is a conjunction. Bring down that left-hand conjunct onto its own line, C. And that's going to follow now from line 3 by simplification. Pretty easy to recognize. Whenever you've got a conjunction, go ahead and simplify it, even if it's an extra step. Happily now, that gives us something useful towards being able to use premise 1. Right, premise 1 says, if we have C or not G, then we get that expression on the right, not P and L. Well, we have C, so according to the addition rule, we can add anything we want. So we're going to add not G onto C using addition, using the wedge, so we can do modus ponens with line 1. Now, again, you have to be really careful here. This does not follow from line 1. This follows directly from line 4 by addition. Again, I want you to think through the reasoning. If C is true, then C or anything will be true because one of the two conjuncts, C, will be true no matter what we add on, whether it's what we add on is simple or compound, and whether that's true or false. This expression, C or anything, will always be true. We chose to add not G because we need that in order to be able to get the antecedent of the conditional in line 1. So you have to use that strategically. So I'm going to kind of star this here. This is like the key step that lets you move forward in this proof. Okay, once we have that antecedent of the conditional in line 1, pretty obviously now we're going to get the consequent of that conditional, not P and L, on its own line. And that's going to follow from line 1 and line 5 by modus ponens. But that in itself is another conjunction, not P and L. And whenever you have a conjunction, go ahead and simplify it. So we're going to get not P on its own line. The left-hand conjunct, we're going to bring that down on its own line. And that's going to follow from line 6 by simplification. Okay, we're getting there. The next thing I notice is that the antecedent of the conditional in line 2 is not P and C. Well, we have C on its own line in line 4. We have not P on its own line in line 7. If we can join those together with a dot using the conjunction rule, that will give us the antecedent of this conditional in line 2. So let's do that. Not P and C. And that now is going to follow from line 4 and line 7 by conjunction. Excuse me. Once we have not P and C, that's the antecedent of the conditional in line 2. So if we apply modus ponens on line 2 and line 8, that will give us the consequent of this conditional in line 2. That will give us C implies D. And that's going to follow now from line 2 and line 8 by modus ponens. Excuse me. Okay, the next thing I notice is that number 9 is a conditional, if C then D, and on line 4 we know that C is true. Oop, use the same color here, excuse me. There we go. Because C is true, we know D has to be true, and this is a very easy step to recognize. This is review at this point. So this follows from line 4 and line 9 by modus ponens. Now we're almost done with this proof. The next thing I notice is that the conclusion is D or R. And we know D is true, and we already said that according to the addition rule, you can add anything you want onto a previous statement using a wedge, and that new statement will be true. So on line 11 then, which I'm going to do way over here on the right, on line 11, because D is true, D or anything will be true, including D or R. and that's going to follow from line 10 by addition, and we're done. But again, something crucial to notice here is that the right part of this disjunction in the conclusion, R, doesn't appear anywhere in the proof. So we know we're going to have to use addition to add that letter into the proof somehow. The question was just, where do we do it? Once we got D on its own line, we can add D or R, add R on D using the wedge, create a disjunction, in other words, and that will be true. Because if D is true, then D or anything will be true. That's what addition tells us, and that's how we got the conclusion. Okay, next example. In this example, we're given 4 premises. Premise 1 says not H implies that not T implies R. Line 2 says either H or E implies F. Line 3 says one of two things is the case, either not T or E. Line 4 says not H and D, so not H is the case and D is the case. And we're trying to show this conclusion, R or F. Let's dive in. Add a new line, line 5. The first thing I notice is that line 4 is a conjunction, not H and D. And one of the easiest first steps is to simplify that conjunction. We're going to bring down the left-hand term, not H, on its own line. That's going to follow from line 4 by simplification. And that lets us do a couple of really easy next steps, I think. On line 1, we've got if not H, then that expression in parentheses. Well, on line 5, we know not H, so we can use modus ponens to get that expression in parentheses. Not T implies R. Hopefully that is easy in review at this point. If not, go back up to the video from the previous week and review modus ponens. Okay, so this is going to follow from line 1 and line 5 by modus ponens, MP. Okay, well, line 2 tells us that either H is the case or E implies F. Well, we know H is false. That's what we found out on line 5. So from that, using disjunctive syllogism, we can get E implies F. Right? Line 2 says either H is the case or that expression in parentheses, but we know H is false. So the expression in parentheses, E implies F, has to be true. That's going to follow from line 2 and line 5 by disjunctive syllogism, DS. Okay. The rest of this proof should be pretty straightforward, but it's going to depend on your ability to see something. What I notice next is that the conclusion is a disjunction, and one way you can get a disjunction is through a constructive dilemma step. So I'm looking for a constructive dilemma here that we might have to build in order to be able to use constructive dilemma. What I see is that we have a disjunction on line 3, not T or E. The next thing I notice is that each of those two terms implies something. Line 6 says not T implies R. Line 7 tells us that E implies F. And this is really starting to look like a constructive dilemma. We've got a disjunction, and each of those two terms implies something else. But in order to be able to use constructive dilemma, I have to conjoin those two conditionals together. And because we have not T on the left hand of this disjunction on line 3, I'm going to start with the conditional on line 6. So on line 8, I'm going to write not T implies R. That's the part that comes from line 6. Use a dot, and we're going to have E implies F. That came from line 7. So again, that's going to follow from line 6 and line 7 by conjunction. Basically, we took the conditional on line 6 and the conditional on line 7, connected them together because we're setting up a constructive dilemma. In order to use constructive dilemma, you have to have two conditionals that are connected together with a dot. It's part of how this textbook defines constructive dilemma. There are actually other ways of defining constructive dilemma. Some books don't require you to connect the conditionals together with a dot and just let you cite 3 premises. But this book forces you to connect those two conditionals together with a dot before you can use constructive dilemma. And I want you to do the same thing on your homework. Okay, so now that we have those two conditionals conjoined together, again, I'm going to use a different color here because I want to draw explicit attention to the reasoning going on. Right, line 3 tells us that either not T is the case or E is the case, right? That's what line 3 tells us. Now line 8 says each of those two terms implies something else. Not T implies R and E implies F. And if one of those two antecedents is true, one of the two consequences has to be true, R or F. right? Which, again, are just to be really clear about this, which are the two consequents right here, R and F. And that's going to follow now from line 3 and line 8 by constructive dilemma, CD. And we're done. We've shown that the conclusion follows from the premises by necessity. This argument is a valid argument, in other words. Okay. Okay, so before we move on, just to be really clear, in order to be able to use this rule, constructive dilemma, you have to have a disjunction and you have to have two conditionals conjoined together, and the antecedent of those conditional have to be the two disjuncts of your disjunction on a separate line. If you don't have that, you can't use constructive dilemma correctly. And in order to use constructive dilemma, then you might have to set up the form of a constructive dilemma, which is what we did here on line 8. In order to have those two conditionals conjoined together with a dot to match the form of the rule constructive dilemma from your textbook. Okay, let's move on. This is a fairly scary looking argument. We have 5 premises now and a conclusion. The first premise says, if M or N, then F implies G. Line 2 tells us that D implies not C. 3 says not C implies B. Line 4 tells us that 2 things are true, M and H. 5 says one of 2 things is true, either D or F, and we're trying to show this conclusion, either B or G. Let's dive in and see if we can figure out how to do this. Okay, the first thing I notice is that we have a conjunction on line 4, M and H. And if M and H is the case, then M would have to be true. That's going to follow from line 4 by simplification. Now, obviously, H would be true as well, but you don't have a rule that lets you do that yet. In order to do that, H would have to be on the left, and H is not on the left here. Okay. This next step might require a little bit of inspiration, a little bit of insight, a little bit of pattern recognition. I noticed that on line 1, we've got a conditional. If M or N, then F implies G. So if we can get M or N, we can do modus ponens on that. Well, how can we get M or N then, should be the question that you ask yourself. Well, if we have M on its own line, we can use addition to add anything we want using a wedge, and that will follow. So because we have M, we can have M or N. And that does not follow from line 1, that follows directly from line 6 by addition. But the reason we did that, the reason we chose to add in on as opposed to adding something else on, the reason we chose to do it right here is so we can get the antecedent of this conditional way up here on line 1. And if you don't see that, you're going to get stuck and you won't be able to complete this proof. So make sure you pay attention to why I did that. And I'm doing it strategically to give me the antecedent of the conditional in line 1. Well, from there, we said we can do modus ponens to get that expression in the parentheses on the right in line 1. That's going to give us F implies G. That's going to follow now from line 1 and line 7 by modus ponens. Okay. Let's see here. The next thing I see is that I notice on line 2 and 3, we've got a pattern here. Not C is kind of a middle term. D implies not C, but not C in turn implies B. And we can use hypothetical syllogism then to get D implies B. And hypothetical syllogism is one of the rules from last week. Basically 2 conditionals. The one term is the antecedent of one is the consequent of the other. So you have a middle term. We've got, let's see, that's going to follow from line 2 and 3 by hypothetical syllogism. Okay. Moving on, this next step might require a little bit of inspiration. What I see is that the conclusion here is a disjunction of 2 terms, B or G. And we have B or G right here in lines 8 and 9 as the consequence of 2 conditionals. So it's starting to look like a constructive dilemma. We know that D or F is the case. Well, F implies G and D implies B. So if either D or F is true, we know that either B or G would have to be true. This is looking a lot like a constructive dilemma. We just have to set it up as a constructive dilemma. In order to use constructive dilemma, those 2 conditionals on line 8 and 9 have to be conjoined together with a dot. And because B is the left-hand term here, we're going to start with line 9, which will give us B on the left. So we've got D implies B. That's the statement from line 9. And F implies G. And that's going to follow from lines 8 and 9 by conjunction, C-O-N-J. Make that a little cleaner, C-O-N-J. It looks like an M. C-O-N-J. There we go. Okay, so now we've got our constructive dilemma. And again, I'm going to be a little granular in showing this to you. Line 5 says one of two things is the case. I'm circling it here in green, either D or F, right? Either D or F. Line 10 tells us that D implies something and F implies something. D implies B and F implies G. So if one of those two antecedents is true, D or F, now I'm going to use a different color here just to draw explicit attention to this. If one of those two antecedents is true, one of the two consequents would have to be true, B or G. And that, happily, is the conclusion that we need. So on line 11, I'm going to write it up here off to the side. On line 11, we know B or G. Now, where does that follow from? Here you have to be really careful. That follows from line 5, that's our disjunction, and it follows from line 10, which is that conjunction of the two conditionals. So line 5 and 10 by CD, constructive dilemma. And we're done. We've shown that the argument is a valid argument. So there were a couple of really key steps you had to notice here, and I'm gonna circle them in yet a different color. I'm gonna circle them in white here just to make it really easy to see. You had to notice this addition step right here on line 7. If you didn't notice that, you wouldn't be able to get your way through this conclusion. And you had to notice that you needed to do this constructive dilemma step, which is why we did line 10. If you didn't see those two things, you wouldn't be able to work your way through this proof. So again, if any of those steps is unclear, go really slowly through this proof. Back the video up, pause at every step, and make sure you see not just what step I did, but why I did that step in order to be able to reach the conclusion. You have to be able to notice that. And in general, proofs are going to be like that. You have to be more and more strategic as the proofs get more complex and as we get more and more deduction rules. Okay, let's do a couple more examples. The first premise here is fairly scary looking, but I predict it won't be here in just a moment. It's a conditional. The horseshoe right here is the main operator. It says if k is false and n is false, if not k and not n, then this long expression in parentheses that we don't need to worry about just yet, or brackets. Line 2 says k implies n. Line 3 says not n and b. Line 4 tells us either not p or not r. And we're just trying to show the conclusion G, which I'm going to underline right here, just to remind you what the goal is. Never lose sight of the goal, because as proofs get more and more complex, you're constantly going to have to be looking at the conclusion, asking yourself, what can I do that will be productive towards yielding that conclusion? And notice that G is, it is inside the premises, but it's way up here inside this bracket in line 1. So we're going to have to break apart that statement in line 1 somehow. We don't know exactly how yet, but we know that's what we're going to need in order to be able to get that conclusion. Okay, let's dive in. The first thing I notice is that we have a very easy first step on line 3. Line 3 is a conjunction. It says n is false and b is true. And if one of those two expressions is the case, not n and b, the left-hand conjunct has to be the case. So not n, which is right here on line 3. That's going to follow from line 3 by simplification. Okay. From there, something fairly easy is easy to recognize. Line 2 tells us k implies n, but we know the consequent is false. We know not n on line 5. So from Modus tollens, we know that the antecedent has to be false or not k. And that's going to follow from line 2 and line 5 by Modus tollens, MT. Okay. What I recognize next is that in order to be able to start breaking apart this long statement on line 1, which is a conditional, we're going to need this antecedent on its own line. We're going to need not k and not n on its own line. Well, we have not n and we have not k. All we have to do is conjoin them together. Not k and not n. That's going to follow from line 5 and line 6 by conjunction. And the whole reason we did that is so we can get the antecedent of this conditional up here on line 1. And the reason we did that is so we can do this next step. So we can do modus ponens and get this expression in brackets on its own line, which I'm going to rewrite here. Not P implies K, and not R implies G. Okay, that's going to follow now from line 1 and line 7 by modus ponens. Okay, we're very nearly done with this proof. Let's see what we're going to do here. What I notice next is that line 8 is the conjunction of two conditionals. It says not P implies K and not R implies G. And we know that one of those two antecedents has to be true. Line 4 tells us that. I'm going to circle that in a different color here. Line 4 tells us that either not P or not R. And line 8 tells us that one of those two, each of those two terms, not P and not R, implies something else. And that already matches the form for constructive dilemma. So if one of those two antecedents has to be true, not P or not R, we know that one of the two consequents, K or G, would have to be true, which I'm going to write on its own line, K or G. And that's going to follow now from line 4 and line 8 by constructive dilemma, CD. Okay, we're almost done. We're trying to get G on its own line. Line 9 tells us that either K is true or G is true. Like one of those two expressions has to be true. But line 6 tells us that K is false. So we have the negation of one of the two disjuncts. From there, we know that the other disjunct has to be true. So if K is false, G has to be true. And that's going to follow now from line 6 and line 9 by disjunctive syllogism, which was one of the rules from last week. And once we have G on its own line, we're done, and we'll have shown that this argument is a valid argument. There we go, and we're done. Fairly straightforward. This one wasn't too bad, but in order to move forward through this proof, you had to be able to, in fact, I'll indicate it here in a different color. You had to be able to recognize that we needed to do this constructive dilemma step. If you didn't recognize that constructive dilemma step with lines 4 and 9 there, you wouldn't be able to move forward with this proof. Okay. Next example. We have 4 premises. Line 1 says 2 things are the case. J implies K, and with a dot, not O implies not P. Line 2 says L implies J, and not M implies not O. Line 3 says if not K, then L or not M. Line 4 says not K and G, so not K is the case and G is the case, and we're trying to show not P. So add a new line. There are a few things we can do, but I see one easy starting point. Line 4 is just a fairly straightforward conjunction, not K and G, so we can bring the left-hand conjunct down on its own line, not K. And that's going to follow from line 4 by simplification. Right? Obviously, if not K and G are both the case, then not K on its own is the case. Pretty easy to understand. Okay, once we have not K, line 3 tells us that not K implies something. Not K implies that expression in parentheses, L or not M, which we're going to write on its own line, L or not M. This is all review at this point. That's going to follow from line 3 and 5 by modus ponens. Okay. The next thing I notice is that on line 1 and 2, we have conjunctions, and we can simplify those and bring those conjuncts down on their own lines. So for example, on line 7, we can bring down the left-hand conjunct from line 1. J implies K. And that's going to follow from line 1 by simplification. And I'm actually going to do the same thing with line 2. Line 2 is also a conjunction, so we're going to bring the left-hand conjunct down. L implies J. And that's going to follow now from line 2 by simplification. Okay, the next thing I see is that on lines 7 and 8, we have two conditionals. Line 8 says L implies J, but line 7 says that J in turn implies K. So according to hypothetical syllogism, we know that L has to imply K. That's going to follow now from line 7 and 8 by hypothetical syllogism. But we know K is false, right? Line 5 tells us that. In other words, the consequent of the conditional in line 9 is false. So we know that L has to be false. The antecedent of that conditional has to be false. And that follows from line 9 and line 5 by modus tollens. Actually, just to keep it clean, I usually write the lowest number first. There's no real rule about that as long as you cite both lines. But let's cite the lowest number first. This would be 5 and, oops, wrong color. This would be from line 5 and 9. There we go. Oop, still the wrong color. Sorry. It's a bit of a challenge to switch colors on the iPad like this. Line 5, there we go. Line 5 and 9. The next thing I notice is that on line 6, we've got a disjunction. Either L is the case or not M is the case. But line 10 tells us that one of those two disjuncts, the first one, is false. L is false. So the term on the right, not M, would have to be true. So on line 11, not M has to be the case. And that follows from line 6 and line 10 by disjunctive syllogism. The next step might be a little tricky to notice. Line 2 tells us that two conditionals are true. L implies J and not M implies not O. And we know that one of those two antecedents has to be the case. Either L is the case or not M. That's what line 6 tells us. And that looks like a constructive dilemma step. So from there, we know that one of the two consequents, J or not O, would have to be the case. J or not O would have to be the case. And that follows now from line 2 and line 6 by constructive dilemma. But notice what we have in line 1. Line 1 tells us that each of those two terms, J or not O, implies something else. J implies K and not O implies not P. And so we can do another constructive dilemma right after that to get the two consequents of the conditionals in line 1, K or not P. K or not P. And that's going to follow from line 1 and line 12 by constructive dilemma. Oop, I'm sorry, I just realized I cited the wrong rule here. This should be CD, constructive dilemma. There we go. Quick correction. Okay, we're almost done with this proof. Line 13 tells us that K is true or not P is true, but we know K is false here on line 5, so that means not P would have to be the case, and that's the conclusion that we're trying to show. And that would follow from line 5 and line 13 by disjunctive syllogism, DS. And we're done. Where you might have got stuck in this proof is recognizing that you can do these constructive dilemma steps using those premises on line 1 and line 2 and using the disjunctions that go along with them. If you didn't see those constructive dilemma steps, you would have got stuck in this proof. Okay, moving on. In the next example, we have 4 premises. If P or S, then E implies F on line 1. Line 2 tells us that if P or T, then G implies H. Line 3 tells us that if P or U, then E or G. Line 4 tells us that P is true, and we're trying to show F or H. Okay. What I notice about these premises is that the antecedents of these conditionals in line 1, 2, and 3 are all disjunctions. P or S, P or T, P or U. And we know on line 4 that P is true. And according to addition, you can add anything you want onto an existing statement using a wedge, and you'll get something true. So on line, in fact, I'll do 3 steps in one here just to make this really easy to see what I'm doing. We're going to get P or S, we're going to get P or T, and we're going to get P or U. And those are going to follow, all of those are going to follow from line 4. So line 4 by addition, line 4 by addition, and line 4 by addition. And we're doing those steps so we can get the antecedents of these conditionals in lines 1, 2, and 3. And now we can do modus ponens steps. Once we have those 3 antecedents, we can do modus ponens using the conditionals in line 1, 2, and 3. So from line 1 and 5, we're going to get E implies F, the consequent of that conditional in line 1. So line 1 and 5, modus ponens. From line 2 and line 6, we're going to get the consequent of the conditional in line 2, G implies H. So 2 and 6 by modus ponens. Always happy when you see a modus ponens step. And from line 3 and 7, we're going to get the consequent of the conditional in line 3, E or G. From line 3 and 7 by modus ponens. Okay, the next thing I notice is that if you look at lines 8, 9, and 10 now, it's starting to look an awful lot like a constructive dilemma. You've got a disjunction here in line 10. It says either E is the case or G is the case. Line 8 tells us E implies something. Line 9 tells us G implies something. So if one of those 2 antecedents is the case, one of the 2 consequents would have to be the case, F or H in other words. And happily, that's just the conclusion that we're trying to show. All we have to do is set up a constructive dilemma step to be able to get that conclusion. In order to use constructive dilemma, those 2 conditionals have to be conjoined together on a single line. So we're going to need E implies F and G implies H. Those are those 2 conditionals on line 8 and 9. So 8 and 9 by conjunction, C-O-N-J. Now we can do constructive dilemma just to drive the point home here. In fact, I'll use this blue color again to drive the point home. 10 says E or G. Either E is the case or G is the case. Line 11 now says E implies something and G implies something. So if one of those 2 antecedents is true, one of the 2 consequents would have to be true, either F or, not F or G, F or H. One of the 2 consequents, which I'm going to indicate here in green, F or H. Okay, and that's going to follow from line 10. It's changing color. From line 10 and line 11 by constructive dilemma, and we're done. We've shown that that conclusion follows. So there were a few key moves here. You had to recognize that you needed to do these addition steps, and you had to set up constructive dilemma properly by doing that conjunction step on line 11. If you missed any of those steps, you wouldn't be able to work your way through this proof. So again, of all the rules that you've got, addition and constructive dilemma are probably both the hardest to recognize, and also it's very important that you use them strategically, doing whatever preliminary steps you need to do in order to be able to set up that constructive dilemma. Okay, a couple more examples. Here we have 3 premises. D implies B and C implies D on line 1. Line 2 tells us that B implies D and E implies C. Line 3 says either B or E, and we're trying to show that D or B follows from that. So let's add a new line, line 4. Okay, what I notice here is that lines 1 and 2 are both conjunctions. The dot is the main operator of both of those statements. So because those are conjunctions, we can simplify and get each of those 2 left-hand terms on their own line. D implies B. I'm just going to do them at the same time here. B implies D. Okay, and those are going to follow from line 1 by simplification, and line 2 from simplification. And those may not both be necessary, but they're good, easy first starting points, and I think it's always better to do the easy stuff first and then go looking for things that are harder to do. Let's take a look at what we can do next. Okay, the next thing I notice is that on line 2, we have the conjunction of 2 conditionals. B implies D and E implies C. And we know that one of those two antecedents is true. On line 3, either B is true or E is true. So by constructive dilemma, we know that either one of those two consequences has to be true. Either D or C would have to be the case. And that would follow from line 2 and line 3 by constructive dilemma. Okay, also the next thing I notice now, very similarly, line 6, the line we just added, tells us that one of two things has to be the case. Either D is true or C is true. And line 1 tells us that those two disjuncts each imply something. D implies something here in line 1, and C implies something here in line 1. So by constructive dilemma, we know that one of the two antecedents here, B or D, would have to be the case. So B or D would have to be the case. And that's going to follow now from lines, let's see, that's going to follow from line 1 and line 6 by constructive dilemma. Now we're close to getting the conclusion. We have B or D, but we need D or B. And obviously those are equivalent to each other, but we don't have that rule yet. So we're not done until we get exactly D or B on its own line. Let's go looking for how we might do that. Okay, line 4 tells us that D implies B, and line 5 says that B implies D. And we know that one of those two expressions is true, B or D. So I can actually set up a new constructive dilemma using those conditionals in lines 4 and 5 and that disjunction on line 7. So what I'm going to do is take the conditionals on line 4 and 5, starting with the one on line 5, because that's the left-hand term of this disjunction in line 7. So B implies D, and D implies B. And that's going to follow from lines 4 and 5 by conjunction, C-O-N-J. Okay. So by another constructive dilemma step now, line 7 says B or D, and line 8 says each of those two terms implies something. B implies D, but D implies B. So one of these two, I'll use a different color here so you can see it, one of these two consequences would have to be the case, D or B. Oops. Thought I'd changed color, but I didn't. D or B would have to be the case. And that's going to follow now from line, let's see, line 7 and 8 by constructive dilemma. And happily now, we have D or B in the correct order, and we are done. So that argument is a valid argument. Okay, last example for this week's video. And then, like I said, I want you to get lots of practice doing proofs. I want you to do all of your homework exercises. If you have time, redo the proofs that I'm doing in this video and do the sample proofs from the textbook chapter as well. Okay, this is a fairly scary looking argument. Hopefully it won't take too many lines to do, but let's dive in. Let's see what we can notice here. I only see one really obvious starting point. I see that in line 5, we've got a conjunction, not Q and H. And if that's the case, we know not Q has to be the case. The left-hand term of that conjunction has to be true. So that's going to follow from line 5 by simplification. Okay. Well, line 4 says that either Q is true or S is true. And if we know Q is false, that means S has to be true. And that's going to follow from line 4 and line 6 by disjunctive syllogism, DS. Okay, from here, I notice that the antecedents of these conditionals in line 2 are both disjunctions. Like the antecedent of line 2 is S or F, and the antecedent of line 3 is S or G. And we have S, and we know we can get S or anything by addition. So we're going to do 2 addition steps back to back. I'm going to do them together so you can see what I'm doing. From line 7, not from line 2 or 3, but from line 7, I'm going to get S or F by addition and S or G by addition. I'm choosing to add F or G, F and G by the wedge onto S. Again, just to be really clear, from S, you can get S or anything. That's what addition tells us. If S is true, then S or anything would have to be true. So that's going to follow from line 7 and line 7 here by addition. And I'm doing that so I can get the antecedents of these conditionals up here on lines 2 and 3. If you don't see those steps, you're probably going to get stuck on this proof. Okay, so now I can do 2 modus ponens steps. I've got the antecedents of the conditionals in lines 2 and 3. So from line 2 and line 8, I can get Q or W by modus ponens. Let's see, that was 2 and 8 by modus ponens. And on line 11, I can do another modus ponens step with lines 3 and 9 to get the consequent of the conditional in line 3. Not Q implies X. And that is going to follow from line 3 and line 9 by modus ponens. Okay. Add a new line, which I'm going to bring way up here just to give us a little working space. I doubt we'll need that much space, but you never know. The next thing I notice is that there are a couple things we can do with line 6 because we know that Q is false. I'm going to do the obvious steps. Even if we end up with some extra steps, that's usually okay. I'm going to do the obvious stuff. So once we know Q is false, 10 tells us that Q is true or W is true. We know that W would have to be true because Q is false. That's going to follow from line 6 and line 10 by disjunctive syllogism. I also notice that once we have not Q, we can get X on its own line. That's going to follow from line 6 and line 11. 6 and 11 by modus ponens. Now, the reason that's important is that in line 1, the antecedent of that conditional is W and X. And now we have W and X on their own lines in line 12 and 13. If we can join those together with a dot, we'll have the antecedent of that conditional in line 1. So W and X. And that now, be really careful here. That doesn't follow from line 1. That follows from line 12 and line 13 by conjunction. Okay? And once we have W and X, we can do modus ponens together with line 1, and that will give us Q or R, the consequent of that conditional in line 1. That's going to be from line 1 and line 14 by modus ponens. You can see the proofs are starting to get longer and longer, and that's going to be true from here on out. Okay? Remember, the goal here is to get R on its own line. Don't forget about what the conclusion is. Line 15 says one of two things is the case. Either Q is true or R has to be true. That's what a disjunction means on line 15. But way back here on line 6, we know that Q is false. So because Q is false, we know that R has to be true. And that's going to follow now from line 6 and line 15 by disjunctive syllogism. And we're done. We got R on its own line, and we've shown that this is a valid argument now. And it took, it took 11 additional steps. This is the last example I wanted to do. So just to reiterate a few things here. Unlike last week when the proofs were fairly linear, as long as you started to apply each rule kind of in order, you'd get to the conclusion. You can see here that now that's not as true as it used to be. In order to achieve the goal, to reach the conclusion on its own line, you have to set up certain steps. You have to be able to see that you apply an addition step so you can do something else. Like here, we applied addition so we could do modus ponens using those conditionals on lines 2 and 3. We also, if we need constructive dilemma, we might have to set up a constructive dilemma by taking those two conditionals that you need and conjoining them together so you can set up a constructive dilemma that matches the form of the rule. And you have to be able to recognize those things in order to be able to sort of brute force your way through these proofs. Like I said earlier in the video, if you need any help on this, don't be afraid to let me know. Contact me by email, and we can jump on a Zoom meeting and do some examples together if you find yourself, confused or not seeing, how to apply the rules correctly. If you find yourself stuck anywhere, oftentimes, getting stuck is a normal part of doing a proof. You'll find that you've applied a few rules correctly, added a few more lines to the proof, and then you just don't see what to do next. And part of what's inherently challenging about doing proofs is kind of waiting it out, getting stuck and then, waiting for a little bit of inspiration to see what you can do next. Hopefully the combination of applying the rules that you see you can apply, constantly looking at the conclusion to remind yourself what kinds of steps are going to be, fruitful or conducive towards getting that conclusion. Hopefully those two things together will come together and you'll kind of be able to get yourself unstuck by seeing what you can do to move forward in a proof. But this is really important to remember about proofs, that just because you get stuck somewhere doesn't mean the argument is invalid. All of these are valid arguments. It's just a matter of seeing what you can do, what steps you can apply, and seeing the overall strategies that you're going to be able to take to get to the conclusion, and taking whatever intermediate steps are necessary to set up the key steps of the proof. Like the key steps here of this proof are these modus ponens steps, and if you didn't, or excuse me, these addition steps. And if you didn't see these addition steps, you're going to find yourself getting stuck in the context of a proof, and you won't be able to work your way through the proof. So that's all I have for you for today. Make sure you get plenty of practice on proofs. Again, it's practice, 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 practice. Get your homework to me by the end of Sunday at 11:59 p.m. Definitely be in touch if you have any questions. Other than that, have a great week and get lots of practice having fun doing some proofs.